Hello ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about a topic which is pretty important in all of your science classes. It's called significant figures. And follow along in your notes, and if you have any questions, please make sure that you ask me tomorrow, because this is probably the most difficult little lesson in this unit. Okay, what exactly is a significant figure and why is it important? The first thing you have to recognize is that anytime we make a measurement in a science class, in fact, anytime you make a measurement outside of a science class, your ability to do so is limited. And it's limited in two ways. The first is by the precision of the equipment that we use. So for example, if I gave you an irregular object and a ruler and said, here, measure the length of it, it might take you some time, you could probably do it, but if I gave you something like this, a industrial sized caliper, which is used, to measure precisely how big or how small certain tiny little components might be in electronics or in cars or in who knows what else, it would probably be easier and more exact if you used something like this than if you used something like that. So the better the equipment, the more precise the measurement. But just because I give you this nice fancy device doesn't mean that you're going to be able to use it appropriately. And so you're also limited by your ability to read the equipment. I mean, some people have problems even using a ruler to measure something, let alone something like this caliper. So what exactly are significant figures then? Well, significant figures are a way for scientists to keep track of how precise their measurements are, and so not to kind of upscale, or I guess even downscale, their results by having too many or too few decimal places in their answers. Okay, so significant figure rules. Now, these are going to seem like arbitrary rules, but they're not. There's a purpose behind each one, and each one is kind of an important little step in making sure that our measurements are as precise as we say they are. So the first rule is the obvious one. Non-zero digits are significant. So that means that anytime I make a measurement and there are no zeros involved, so like 38.15, 5.6, 65.6, 122.55, every single number that I listed there is significant. So how do we count significant figures? You literally count how many numbers there are. And so since they're all non-zero, it's nice and easy. I've got 4 numbers, so I have 4 significant digits. Here I have 2, so I have 2. Here I have 3. And then I have 1, 2, 3, 4, 5. Okay? So every single number in every single one of these measurements is significant. Now, what about those pesky zeros? So, leading zeros. Now, when you hear the word leading, that's exactly what it sounds like. Those are zeros that appear in front of things. Now, you might take a look at this list and say, hey, none of these are like greater than 1. Okay? Like, for example, let's say the number 65. Okay, that's a number that definitely is greater than 1. I could put a whole bunch of zeros in front of it, but that's still 65. Okay, so the reason why you don't see any are because these zeros, we never write them in front anyway. They're just considered, if we did, it would be considered, improper. So leading zeros are not significant. What does that mean? We don't really count them. Now, that doesn't mean that we ignore them. That just means that when we're actually trying to figure out how precise a measurement is, these leading zeros, wow, I don't know why my marker did that, but these leading zeros at the beginning are just kind of arbitrary. They're just telling us how small something is. The more zeros, the smaller the measurement. Okay, so that's not really giving me a lot of information. So here, I only have one non-zero number, and so I only have one significant figure. Here I have 3, here I have 2, and then here I have 4. And if I wanted to add in my 65, I would only have 2. But these leading zeros are not significant. All right, so rule number 3 is not exactly a scientific term. It's called a sandwiched zero. I made up that word, okay, because it's kind of like a sandwich, for lack of a better term. That's why I say sandwich zeros. Zeros that are sandwiched between non-zero numbers or decimals are significant, so they're all important. What does that mean? Take a look at the zeros that appear in these examples. Not all of them, but just, some of them. That zero, it's sandwiched between a 5 and a decimal point, and an 8 technically. And so that 0 is now significant. So if I were to count, I would count every single one of these numbers. And so I would have 4 significant figures. Next up, these zeros. They're trapped between the 2 and the 1. In fact, one of them is trapped between, a decimal point there as well. So every single one of those zeros becomes significant. All right? And so that means that I have 1, 2, 3, 4, I have 5 significant figures there. Now take a look at this next one. This 0 is not sandwiched. It's a leading 0. It's at the beginning of something. Okay? So that 0 still doesn't matter. But this 0 is trapped between a 7 and a 0, a 7 and a 2, and so there are 3 significant figures here. And then last but not least, this 70,000 and a decimal point. Every single one of those is significant because it says zeros that are sandwiched between non-zero numbers or decimal points. And so that little decimal point, which I tried to point out, and it doesn't really look like I'm pointing it out very well, but that little decimal point right there, that makes all the difference. All right, and so here is rule number 4, the one that causes people the most problems. So trailing zeros. So remember, we had leading zeros, those appeared at the beginning of a number. Trailing zeros appear at the end of a number. Now the reason why this one is confusing to most people is just because there are 2 parts to it. So if a number does not have a decimal, these trailing zeros are not significant. So let's take a look at these examples here. So this doesn't have a decimal point, this doesn't have a decimal point. So these zeros that appear at the end, they are not significant. That means that for this first one, I only have 2 significant figures, the 2 and the 5. Here, I only have 1 significant figure. Now, what about if there is a decimal point? If there is a decimal point, then all of those zeros become significant. So let's take a look at these guys. All right, so I've got 25.00. There's a decimal point. All of them are important. All of them are significant. Same thing here. Okay, I have a sandwiched 0 right between an 8 and a decimal and a 6. And then here I have these trailing zeros. All of them are significant now. So I actually have 6 significant figures. And then here again, I've got 600.0. This 0 is a trailing 0. It appears at the end of a number, and there is a decimal point. It must be significant. So I have 4 significant figures. Now again, why? Okay, just let's actually get at the heart of the question here. Most people are saying, why? Why does having a decimal here make all the difference? So let's pretend you stand on a scale, and the scale says you weigh 125.0 pounds. It's a pretty good scale. What if you stand on a different scale and it says you weigh 125.0000 pounds? Which scale is more precise? Obviously this one. Why? It gave you not just 1 decimal point, it gave you 4 decimal points. And so if you think about it, okay, what this is saying is you weigh about 125 pounds. It could be 125.1, could be 124.9. This is telling you you weigh 125.0000 pounds, maybe 125.0001 pounds, or maybe 124.9999 pounds, but that is much closer to just 125. Okay, so that's the reason why a decimal point makes all the difference. Okay, if you have a decimal point, these zeros become extremely important because they're telling me that you made a very precise measurement. Next up, final rule. And this rule is just kind of a bonus rule. It's not really used very often, but if you're doing math with these rules, then it becomes important. Counting numbers, defined constants, and conversion factors have an infinite number of significant figures. Now you might think that seems weird. Okay, here's the reason why. 100 apples, I can count 100 apples. I can physically count them. They have as many significant figures as I want. They have an infinite amount of significant figures. You might think that seems weird, but think about it. If this was instead 100 grams, it would only have one significant figure. Because 100 grams, I'm measuring that. I'm not counting it. I don't know exactly that it is 100 grams. I just know it's about 100 grams. So that's the reason why counting numbers are different from everything else. And that goes the same for molecules and stuff like that. Anything that you can count, apples, molecules, pencils, phones, whatever you can think of, those all have an infinite amount because they can be counted. Defined constants, things like pi. Yes, we round pi to 3.14 almost all the time, but technically it has an infinite amount of significant figures because I can go on forever, okay? It doesn't stop. And then finally, conversion factors. Again, because these numbers, like especially this one right here, 10 to the third meters equals 1 kilometer, that's defined. That is a conversion factor that you can look up in a book. That's a conversion factor that you can, actually find online. And so we know exactly that is the relationship between those two numbers. And so again, it has an infinite amount. Why, again, if we were just measuring them, if instead it was just 1 kilometer, that would only have one significant figure. And so again, that means that it would throw off a lot of your math. Again, this is an example of a conversion factor. It has an infinite amount of significant figures. So let's go through a little bit of practice with this. So pause it and see if you can actually answer these. All right, let's take a look at how you did. So this one would have 2. This one would have 4. This one would have 2. All right, and I'm going to stop and skip down all the way to the bottom. That last one has 1, and we'll get back to these two. Okay, so why only 2 here? These are our significant digits. These are leading zeros. They don't matter. Okay, that decimal point made all the difference. Same thing here. Okay, these zeros, this one is a sandwich 0, so it has to be significant. This one, though, is a trailing 0, but there's a decimal point. What about this last one? Well, not last one, but letter C. I've got 650. Only the 6 and the 5 are significant. That 0, there's no decimal point, so that last 0 is a trailing 0 without a decimal point. It doesn't matter. And then the same thing with this. These are all leading zeros. Leading zeros are not significant, so there's only 1. What about scientific notation? We kept saying, hey, we like writing things in scientific notation. How are you supposed to deal with those kinds of situations? Well, remember, these are just telling us how big or how small a number are. So all they're doing is they're just moving our decimal place around. They're not actually doing anything to the number. So really, all I have to look at is I have to look at these numbers. So here I've got 3.00. Every single one of those is significant. There are 3 significant figures. Again, these trailing zeros, because there's a decimal point, they're significant. Next, I have a sandwich 0 here, and I have a trailing 0 here. Again, all of those are significant. Oops, I have 4 significant figures there. This is going to seem like a long video, but trust me, it'll come in handy. So adding or subtracting, what is the purpose behind using significant figures? It seems like 5 arbitrary rules. Why do we care how many significant figures things have? Because we actually do things like adding and subtracting or multiplying and dividing with numbers. And so I want to make sure that I don't just have a whole bunch of decimal places that I don't need in my answers. So for adding and subtracting numbers, your final answer, must have the same number of decimal places as the measurement with the fewest decimal places. So get out a calculator. I'm not even joking. Get out your actual real calculator and plug this simple math problem into it. 25.2 plus 1.34. What does your calculator say the answer is? It says 26.54. These are meters, so I need to make sure that I have a unit in my answer. This is wrong. Okay? Now you might think, hey, how can my calculator lie to me? It's because this is not following the rule for when you add and subtract numbers. My answer has to have the same amount as the fewest. So this has 1 decimal place. This has 2 decimal places. I only need 1 decimal place in my answer. The actual correct answer is 26.5 meters. You might think again, what's the point? Who cares if I just have this here? I would be giving the illusion to the person that I was presenting this data with that I was actually being more precise than I really was. I can only be as precise as my least precise measurement. This right here only has one decimal place. Therefore, I can only have one decimal place in my answer. Plug these guys into your calculator, and it'll make a little bit more sense probably with that first one. 25,000.000 centimeters plus 7.0 centimeters. You know as well as I do, your calculator doesn't care about these zeros. So what is it going to do? It's just going to give you a flat answer of 25,007. Okay, and again, we need a unit. I have to have units. So centimeters. Now let's think about this. Okay, I have to be as precise as my least precise measurement. So right here, I don't have any decimal places in my answer. Here, though, I had 1, and here I had 3. So I need one decimal place in my answer. How am I going to do that? 25,007.0 centimeters. Now this is the opposite problem. Think about it, okay? Here, my calculator is telling me I'm being less precise than I really was. Here, I'm being way more precise because I have that decimal with the 0. What about 25,000 centimeters minus 5.00 centimeters? Again, your calculator is just going to say, hey, I don't care about those zeros. So it's just going to say 2,495 centimeters. Okay? Again, I can only have as many decimal places as my least precise measurement. This has no decimal places. This has 2 decimal places. So I can't have any decimal places in my answer. And guess what? Your calculator has no decimal places in its answer, so technically it's correct. Every now and then your calculator will actually do it accidentally correctly, but remember, it doesn't know anything about decimal places or about significant figures. Alright, so what about multiplying and dividing? Well, this is where the significant figures come in handy. So your answer must have the same number of significant figures as the measurement with the fewest significant figures. So if we're adding and subtracting, we just cared about decimal places. Now for multiplying and dividing, I actually care about significant figures. So try this in your calculator. So again, we've got 2.00 centimeters times 7.00 centimeters. Again, you know as well as I do, these zeros, your calculator doesn't care. So your calculator is just going to say 14, and what would that be? Centimeters squared, because it's centimeters times centimeters. But that isn't true. How many significant figures, not decimal places, but significant figures does this number have? Well, there's a decimal and those zeros are trailing, so I have 3 significant figures. Same here. How many does this answer have? This only has 2. I need to add an extra significant figure. How do I do that? 14.0 centimeters squared. Again, your calculator is giving you the illusion that you were being less precise than you really were. This 0 is extremely important. Try this. 16.0000 centimeters squared divided by 2.0 centimeters. All right, let's try that one out. So what is 16 divided by 2? Again, remember, these zeros, your calculator doesn't care. When you put them in your calculator, it's just going to say 8. 8 centimeters. Why centimeters? Because it's centimeters squared divided by centimeters, so one of the centimeters goes away. All right, so what am I going to do? I need to count my significant figures. Here I have 1, 2, 3, 4, 5, 6 significant figures. Why? There's a decimal point, and all of those zeros are trailing, so it's significant. Here I have 2. How many do I have here? I only have 1 significant figure. I need to add an extra significant figure, so 8.0 centimeters. And that's how we use significant figures and decimal places in order to solve these kind of problems. So here's our summary. Rule 1, non-zero numbers are significant. So you can fill this in your notes. 1, 2, 3, 4, okay, that has 4 significant figures. Leading zeros are not significant. These zeros don't matter. This only has 2 significant figures. Sandwich zeros are, it should say, significant. So that 0, important. These zeros are leading zeros. They're not important. So only those numbers are important. There are 4 significant figures. Trailing zeros are significant if there is a decimal. So here, this has 3 significant figures, there's a decimal. That last one only has 1 significant figure because it's not significant, there's no decimal point. And then last but not least, if you're adding or subtracting, it is the fewest decimal places. If you're multiplying or dividing, it is the fewest significant figures. So plug this into your calculator. What does it say the answer is? So in your calculator, it says 10.35. But this only has 1 decimal place, and this only has 1 decimal place. So I can only have 1 decimal place in my answer. What's the correct answer? 10.4. Try this multiplication out for size, okay? And now you'll see again why this is extremely important. So when you plug this into your calculator, you get a ridiculous answer. It just keeps adding on decimals here, okay? You get that, or something similar to that. Now, how many significant figures does this first number have? It has 2. How many significant figures? The next one, 3. And the next one after that has 2. So I can only have 2 significant figures. So technically the answer here should only be 35. If you would have given me all these decimal places because your calculator told you that was supposed to be there, you'd be totally and completely wrong.